Hydrogen bonds are a type of intermolecular force that exists between molecules that contain HN or HO or HF somewhere within the molecule. Um, so for example, if I were to show you this structure, I would know that this structure would hydrogen bond with another one because it has the OH group. However, if I were to ask you about this one would not hydrogen bond with another because though it has O and H, they're not directly connected to each other. So the ones I'm looking for are HN, HO, and HF somewhere within the molecule. These also are pretty much always in polar molecules. If I were to draw a water molecule, and I'm going to draw it bent how it actually is in 3 dimensions, again, the oxygen has a higher electronegativity, and it ends up being that this side of the molecule is relatively negative, and the H's sides are relatively positive. So if I have another water molecule, the negative side of one is attracted to the positive side of another. And the way that we would indicate a hydrogen bond is generally shown with a dotted line between molecules. So the hydrogen bond is not within a molecule, but it's between two molecules. It has properties of a covalent bond, it has properties of an ionic bond, it has properties of a dipole-dipole. It ends up being that a hydrogen bond or structure that hydrogen bonds is going to be stronger than a dipole-dipole force, which we have already discussed is stronger than a London dispersion force. We see evidence of hydrogen bonding in the boiling point of hydrides. Let me show you some examples. So let's take a look at the red line here. The red line is all related to group 16. So we have H2O, which has that structure. And then we have H2S, which has the same structure, just with S's instead of O's, and then H2SE and then H2TE going down group 16. As we go down the group, in every case, the molecule is polar, and the molecule is polar, and the molecule is polar. So they're all going to have dipole-dipole forces. But as we increase from H2S to H2SE to H2TE, we see an increase in boiling point. And that increase in boiling point doesn't have anything to do with the dipole-dipole force. But as we're getting a larger molecule, that larger molecule has more total electrons, which is giving us a stronger dispersion force. And that stronger dispersion force, or LDF, is what's giving rise to a higher boiling point. Now, water is smaller than H2S. It has fewer electrons. It has a weaker dispersion force, but instead, it has a much higher boiling point. So it has a weaker dispersion force than H2S, but a higher boiling point. And that higher boiling point is due to hydrogen bonds. So in other words, I'm saying that water experiences hydrogen bonding, but H2S, H2SE, and H2TE don't. Okay, we see a similar pattern in the next row. As we go from HCl to HBr to HI, that boiling point is increasing because of a stronger dispersion force. However, HF is out of proportionally higher because, like H2O, it also is going to experience hydrogen bonds. We see the trend as well in nitrogen's column. I've kind of overwritten it a little bit here, so I'm going to do a little bit of erasing. If I look at PH3, ASH3, SBH3, as that molecule gets more total electrons, stronger dispersion force, but NH3 is out of proportionally high because it experiences hydrogen bonding. Now, with carbon's group, we don't see this pattern at all. And so we don't see this pattern at all because none of them hydrogen bond. So instead, we just have a steadily increasing boiling point due to an increased London dispersion force.